Okay.
There you go.
One thing I did not do is the natural log x. I didn't do that one last time. I was going to do it next class. So I'm kind of surprised that it's actually in the homework, but good call. Derivative of natural log x dx. This is one thing you did back in Calc 1. That derivative is 1 over x. Consequently, the antiderivative of 1 over x, okay, is natural log x.
So it'd be 8 ln x? Or
Correct. So this integral, our antiderivative, let me do it now. I'm sorry, I didn't do that last time. I didn't think it was in this first section. Do the antiderivative of 7x, which is 7x squared over 2,
Right.
minus 8 natural log x
Let's see.
plus c. And that would be your answer. We're going
How can you
to,
identify that? Because it's just a constant over x?
yeah, the integration form is the integral of 1 over x dx, okay, is equal to natural log x. We're going to generalize to an absolute value here when we do this, plus c. The 8 you can take out front, and you're left with the integral of 1 over x, which is natural log x. And how do you know this is correct? Take the derivative of natural log x. What's the derivative? Is 1 over x. And that's what this is saying. Okay? Find the function or family of functions whose derivative is 1 over x, and that is natural log x. Okay?
Okay.
I did the e to the x, but I didn't think they did this one here. I thought they did it there with the inverse trig functions that I'm going to do later on too. Good call, though. Any other questions at all?
There was another integration of x plus 7x plus 7, x plus 7 divided by square root of x.
Let's take a look at this one. What you're going to have to do in a problem like this is separate it into two parts. X over the square root of x. Subtract the exponents, you get x to the 1/2 or the square root of x. I'm going to write x to the 1/2. That's this first one. Plus 7 over the square root of x. And that's 7x to the negative 1/2. Okay? And now do each one separately. Okay? And we have a rule for each one of these. Okay, is everybody okay with this? The rule is add 1 to the exponent, give you 3/2, divide by 3/2, which is multiplying by 2/3, okay, plus, that's a negative 1/2 here, just a little mess, 7x, add 1 to the negative 1/2, which will give you a 1/2, divide by 1/2, which is the same thing as multiplying by 2. Okay? Everybody see that okay? What I've done is added 1 to the negative 1/2, giving you a positive 1/2, and divide by the new exponent, which is 1/2. But when you divide by 1/2, you're multiplying by 2. Okay, I'm using this rule. The integral of x to the n is x to the n plus 1 divided by n plus 1 plus c. That's the rule that I'm using, as long as n is not negative 1. When n is negative 1, then we get that natural log, okay? So what do we have here? Negative 1/2 is n. Add 1. That gives you a positive 1/2. Divide by that 1/2, which is multiplying by 2. That's why the 2 ends up there. Your final answer for this question here would be 2x to the 3/2 over 3 plus 14x to the 1/2 plus c. Okay? That's what your answer would be. All right? Does that make sense? Good. Any other questions at all? Now, were you able to look at some of this stuff at all?
No, I wasn't able to yet. I wasn't able to get onto the website.
Okay, so do that when you can. Email me any questions you have.
Yep.
Monday I'll take any questions too,
All right.
as far as that goes.
I gave him most of the formulas, though.
Oh, good. Did you?
Cosecant
Good.
and all that stuff.
Wow.
Just in
Wow. Every day, every hour, Damien, you're moving up the ladder. Wow. Okay, I'm sorry. I don't want to embarrass you. All right. All right. Any other questions on homework? Anything at all?
Can we do this velocity?
Wow. What's this?
Is that the last question in the homework?
The first one. It's the second to last.
Oh.
Okay, let's do it. They give you acceleration is negative 32 feet per second per second. That's what we started with last time. And then they ask you some questions. So we did the derivation last time. So Roberta, with a height of s feet or 5 feet? No, from a height of 5 feet or s feet. I'm not sure if that's a 5 or an s there. Do you know what that is, Melissa? Is that a 5 or an s feet?
5 feet.
5 feet, okay. Initial velocity of 56 feet per second. How high will the ball go? Let's do it. Well, first of all, they give you the acceleration, okay, which is negative 32 feet per second per second. Now, that's what we started with last time. And what we did last time was this. We said, okay, what's acceleration? It's the derivative of velocity. What do we have here? We have a differential equation, dv dt. That's the acceleration. And that's equal to a negative 32. Okay? We got a differential equation. We solved this differential equation for v by doing what? Moving the dt on the other side and integrating each side, taking the antiderivative. When you take the antiderivative or integral of dv, that gives you v. Consider these inverse operations. Okay? You get back the original v. The negative 32 we could take out front. We get the integral or antiderivative of dt, which is t, plus some constant. Okay? Now, what we did last time, we solved for the constant. We said at t equals 0, our initial velocity is v sub naught. So at t equals 0, we ended up saying, okay, so this is 0, this is v sub naught. That gives us c. So we have v equals negative 32t plus v sub naught. Now, in this particular question, v sub naught initial velocity is 56 feet per second. So that's what I'm going to use for v sub naught. So here, v sub naught is 56 feet per second. Okay? So we have velocity is negative 32t plus 56. Okay? But what's velocity? It's the derivative of your position. It's how fast your position is changing. So ds dt is negative 32t plus 56. Again, separate the variables. Throw the dt on the other side. So ds is equal to a negative 32t plus 56 dt. Okay? And we're going to solve for s, the position at any time t, by doing an integral. So let's do it. Okay, how you guys doing? Everybody with me? All righty. Well, let's do it.
Put that back for sure.
Whoa, yes, I can.
Okay.
Okay, everybody okay? All right, so let's integrate each side. Okay. Integral ds is s. That's our position at any time t. The integral of a negative 32t. The negative 32 constant can go out front. The integral of t dt is equal to t squared over 2. Okay, add 1 and divide by the new exponent. That was the rule I just showed you a second ago. We did that rule last time. When you divide it by 2, you're going to get a negative 16t squared. Okay. The integral of 56 dt, take that constant 56 out front, integrate dt to get t. You get 56t plus a constant. Okay, like I said, this is what we did last time. Okay. Now, what do we know? At t equals 0, our position is the original position. That's what we did last time. We did the general result. So we end up with this. S is here. The general result is negative 16t squared plus our initial velocity plus our initial position. Because after all, when t is equal to 0, s is our initial position, s sub naught. This is the general form for position at any time t for one of these kinds of projectile motion problems. This is a projectile motion problem where you're so many feet above the ground, s sub naught feet above the ground, and you throw something up with initial velocity of v sub naught. Okay? This will give you the position at any time t. In this particular problem, v sub naught is 56, s sub naught is 5, okay? Okay, so this is what we get for position at any time t. We want to know how high the ball goes if we were to do this, okay? Well, we want to maximize the position. How do you find the maximum? You take its derivative and you set it equal to 0. Okay, that's Calc 1 problem. You want to maximize something, take the derivative, set it equal to 0. Well, let's take the derivative. When we take the derivative of this, we're finding its velocity. Well, guess what? That's what we had over here for the velocity. And you set it equal to 0. The way it goes. It doesn't come out all that great, but subtract 56. Divide by a negative 32. Divide by 8. Divide by 8. In 7/4 second, we're at our greatest position, our maximum height. At that time, when we're at our greatest height, please note the velocity is equal to 0, which makes sense. We throw this thing up. At its greatest height, the velocity is 0, okay, and then it starts coming down, okay? That occurs at 7/4 seconds. What is that height? What is that maximum height? Take the 7/4, substitute it in for t in our position function. So we got negative 16, 7/4 squared plus 56 times 7/4 plus 5. Listen, this isn't that bad, because this is 49 16ths, and the 16s cancel. So I get a negative 49 plus, it's not too bad. 4 goes into 56, 14 times. 14 times 7, 98. Whoa. Plus 5. You got it? You with me?
See when I run out of room.
At the bottom of the page.
Yes.
You guys are at the bottom of the page too? Well, so am I. All right, when you get this, you get 49 plus 5 is 54. The answer to the problem is 54 feet. Okay? How's it look? Oh, whoa, look at all this other stuff on the other side. Teacher is a bozo and all kinds of weird things. Oh, man. Thanks a lot. You want me to do those? It's your call. It's your call. But here's the rule. The rule is if there's any homework that you tried to do and could not get, ask. Okay? That's the rule. It's up to you.
Sure.
Go ahead. Give me one. Give me all three. Fine.
Well, I have them all written out.
Let's go. Here we go. Here's some questions. First one. First one says the integral of 1 over. What's that?
This last one.
You can have it. Or take it for a while. 3x cubed. Okay. Now, it's 3x quantity cubed. Sorry. I'm sorry. It's 3x quantity cubed. Okay. Which is this. Okay. What you want to do here with a problem like this is take the 1/27th out front, the constant out front, and rewrite this with a negative exponent. Our rule is x to the n, all right? The integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. So you want to get it in that form of x to the n. And the way to do that is to rewrite this as x to the negative third. Okay? You want to get it into that form. So now you do the integral by adding 1 to this exponent and dividing by the new exponent, plus c. Your answer would be written this way, negative 1 over 54x squared plus c. I would assume that's how Course Compass wants you to write it. The x to the negative second, bring it down as x squared. 2 times that is 54. The negative can be anywhere, out front, up top.
I think one of the problems they had that I did, I had a negative exponent on the top, and they marked it right.
Well, they really should. It is right. It seems to me this would be the best form to not write with a negative exponent. They should take all those possibilities, unless they specifically say don't write with negative exponents or something like that. But one of the criticisms that everybody has of WebAssign is they're not specific about the form. And sometimes you'll write a correct answer and I'll mark it wrong because they don't like the form, but not telling you what the form is, and I think that's a little bit silly on their part.
Right.
Yeah. All right, well, there's the first one. The second one is the integral of the cube. Oh, okay.
These are fun.
Cube root of x squared plus 2 dx. It's the same kind of thing. What you want to do is rewrite this now with a fractional exponent, x to the 2/3 plus 2. Integrate x to the 2/3, add 1 to this exponent. That would make it x to the 5/3. When you add 1 to 2/3, divide by 5/3, which is the same as multiplying by its reciprocal 3/5. And the integral of 2 dx is 2x plus c. And that's what you should have. Okay, you okay there, Melissa?
Okay.
Does that make sense?
No, how did you get the 3x with the 5/3 exponent?
Okay, this is 2/3 right now, and the rule is to add 1 to that 2/3. And when you add 1 to 2/3, you're going to have to add 1 in the form of 3/3 to get 5/3.
Got it.
Okay, that's what you got to do. And finally, the last one, you've got indefinite integral with a question mark. It is an indefinite integral. We haven't done any definite integrals yet. We will today. A definite integral is where we have limits of integration, where we use an integral to find that area. We're going to do that today. But right now, you have indefinite integrals where you have this plus c. Okay? And the last one is... this one, x plus 1, 12x minus 1. There is a product rule for derivatives. There's no product rule for integrals per se. There is something called integration by parts, which we will do near the end of the semester. We do basically, well, we do 4.5 chapters, but it's near the end, where we use the product rule, but it's a variation on it. It's not product rule per se. What you're going to have to do with a problem like this is to multiply it out. 12x squared. You have a middle term plus 12x minus x minus 1. Use a FOIL thing here, okay? And now integrate term by term. 12x squared, the integral is 12x cubed over 3. The 11x would be 11x squared over 2. And the integral of 1x, or 1 is x. And then you should simplify 4x cubed. And not much to do there. and that would be your answer. That's what you're going to have to do on something like that.
Okay.
Okay? All right, how are we doing? Any other questions on homework? Oh, I thought you had another sheet. We could have done it. Okay, we all set on that? Okay. Yes?
Did you simplify the 12x?
The 12x cubed over 3, I went 3 into 12 4 times.
But do you have to, or can you just leave it as 12?
You would definitely want to do that. Yes, I'm sure that's a thing where Course Compass should mark it wrong. It should be an automatic process to simplify fractions. Yeah. Okay? Not okay. Okay, go ahead.
You did that like cubed root problem, or the fourth root.
The 2/3 kind of thing I did?
Yeah, when you had like 5/3.
Yeah, that one.
I had a problem similar to that, but I didn't split the fraction when you brought the 5/3 down. Like you
Yeah.
had the 5 on the bottom and the 3 on the side. I just put the fraction at the bottom.
Okay, so you wrote it x to the 5/3 divided by 5/3?
Yeah,
Okay.
and it was,
Yeah,
They took it?
Yeah.
They took it.
All right, I'm a little surprised, because that is definitely not the best form for that fraction.
right.
But they took it. I would,
So what's the bet, what?
this is by far better. Okay, this is a complex fraction here. You don't really want.
So how would you flip the fraction?
Yes.
So-
Yeah, when you divide by 5/3,
Oh, right.
you're multiplying by the reciprocal 3/5. And I'll tell you, on your test, your first test, if I were to give you this problem, there's no way you would see this answer. It would be this answer.
Okay.
So be aware of that, okay? And same,
Because I just found the one that I asked about, and I left it as, mine was 6x to the 3rd over 3, and I just left it like that, and it took that.
and they took that.
Yeah.
Well, I got to tell you, I'm somewhat surprised. On my test, you're not going to see that answer. It'll be a 2.
Okay.
Yeah, it's automatic. And if you put a 2 there, and if Course Compass said that was wrong, I'd be astounded.
Well, I didn't.
That would be a call to our representative, because that to me would be ridiculous. Okay, but I'm somewhat surprised that they do accept that.
Yeah.
It should be an automatic 6 over 3 should be a 2. Dividing by 5/3 should automatically be a 3/5. Okay, that should be automatic. You got another one?
No, that was it.
Okay. Anybody else? All right. How are we doing? All right. It's tough to read. This crowd is tough to read. Yeah, what, you guys all play poker or something here? Or, poker face. No, Vitaly, you don't play poker, okay, Vitaly? All right, please, because your face is an open book. But Nick, I don't know about Nick. I don't know what the heck he's thinking. All right, but anyhow, you ready to go on? Let's go on. All right. What's that?
What is this called?
This is 5-2. This is summation. Sums, okay? We're adding up things. Right now, we're in pursuit of finding the area under some graph of some function. That's what we want to ultimately be able to do in this chapter. Find the area under the graph of some function. Calc 1, we wanted to find the slope of the tangent line. Calc 2, we want to find the area under the graph of some function. Okay? That's our mission here. Okay? And we're going to do that today. That's what we're going to do today. And then Monday, I'm going to do a little proof that shows this connection. We'll do a proof that's pretty interesting, pretty abstract, but I feel obligated to do it, to do a proof actually showing that connection. We'll do that on Monday. But right now, we need to do some things with summation symbols, and that's this symbol. Okay? That's a capital sigma, okay? Greek letter, capital sigma, and it means sum. Find the sum. For example, this notation means find the sum of 4i plus 3 as I goes from 1 to 3. The increment from 1 to 3 is always understood to be 1. So, what this means is start I at 1, 4 times 1 plus 3 plus. Sigma says add these things up. Now let I equal 2. 4 times 2 plus 3 plus. Now let I equal 3. 4 times 3 plus 3. And that would be equal to 7 plus 11 plus 15. And that would be equal to 33. Okay? This is a thing you'll be given. Okay? You'll be maybe given in the first part of the homework is to actually evaluate that sum. Okay? Evaluate that sum. You may get all kinds of possibilities for this sum. All right? You may get something like this. Negative 1 to the I. That index that's changing, could be anywhere and used anyhow. What would you get here? I starts at 1. You would get negative 1 to the first power. That's negative 1. Plus. Now let I equal 2. Negative 1 squared. 1. Plus. Now let I equal 3. You get negative 1 cubed. Negative 1. Plus. Plus. Finally, when I is equal to 100, we end up with a negative 1 to the 100th power, which is 1. Thank you. Okay. Well, what is that sum equal to? 0. Yeah, what happens is the negative ones pair up with all the positive ones, and you end up with 0. Or negative 112. Never mind, don't forget that. Okay, that's an inside joke here with Damien here. All right, all these would pair up, and you end up with 0. Okay, that's how you would do that sum.
Is there any easier way of doing it if it's like 32 to the hundredths?
Wait now. Say that again. Now, what do you got there, Nick? Give me the sum you want to do.
Just saying to change that negative 1 to like a negative 32 or something like that.
Forget it. That would be outrageous, and you wouldn't. Yeah, that web assign, try that thing. Mathematica. Now, Mathematica could possibly do that because you can do summations in Mathematica, but even to the 100th power, if you were to put 100 there with a 32 or a negative 32 in there, I don't know what Mathematica would do, to be honest with you.
I think it's possible.
It's possible, but the numbers get so big, those numbers get huge. I think Mathematica would get bogged down. It may give you an error that after so many iterations, it wasn't any closer to its answer and it's given up. It tells you things like that, all right? So that's a possibility on that. You're going to be asked to do things like this. This is something you will be asked to do, however. Find this sum. Let's go to 100. And something like this. You would be asked to do something like this. Now, this looks pretty nasty. But there are rules. We can break this up into parts. Okay? We can break this sum. Here, let me give you some of the rules, some of the properties of summations here that we can use. Okay? First of all, one property is this. If we have some constant, what we're doing is adding this constant k up n times. What do you think the sum is going to equal here? What is it?
N times n plus 1.
N.
Well, k times k plus 1. Or n times right?
N times k.
There,
N times k is what you get. I know what you're going. You're going for the sum of the first n. I'm getting there. You're a little bit ahead of me. What is this sum? You're adding up k n times. This is k plus k plus k plus k n times. And what is that equal to? nk. Okay? That's what that's equal to. You with me on that?
So how would we do that one?
It's so if you had this second half here, I'm going to give you a rule where we can break this up into pieces, and you got the sum of 3 100 times. What's that sum of 3 100 times? 300. That part of it will be 300. Okay? Okay? I'm going to give you some other rules here, though. Some more rules. If you have a sum, let's say AI here plus B, bless you, bless you. We can break this up into the sum okay. The sum of a sum is the sum of the sums. Okay? Does that make sense? That's one of my favorites, okay? But, yeah, okay? The constant here can be taken out front. Okay? All right, any constant inside the sigma can be taken out front. This b could be taken out front, and we could have ones here. The sum of n ones is n, so we end up with bn here. But we have a rule for the sum of those first n integers. Here, I'm going to go over here now. This is kind of poor planning here on this part. This is equal to 1 plus 2 plus 3 plus n. Now that's a sum you probably should know from tech math. What's that? No, it's not factorials. And we're going to need factorials later on in the course. We won't need the factorials right now, but...
Did we just skip over that one?
Well, no, I'm going to come back to it, but I'm going to give you some properties first, and then we're going to do it with the properties. Okay? Because I don't want to add 1 plus 2 plus 3. I'm going to give you right now, when I give you this property, we'll be able to do that summation. The sum of the first n integers is something you do in tech math, it seems to me.
Yeah.
What's the formula for that? That's the formula you were going for before.
It's over 2, as I said before.
It's over 2.
N plus times n plus 1 over 2.
That's exactly what it is. Okay? That's a formula for the sum of the first n integers. It's n plus 1 divided by 2. This is the one that Gauss did when he was in second grade, right? You know that story of Gauss? I'll tell you the story. Here's Gauss in second grade. You know, in second grade there, they had like 50 kids screaming and yelling, and the teacher would hit them with sticks and swat them and stuff. But to keep the kids quiet, what she did, she gave the kids a problem to do. This problem. Find this sum. Okay? And Gauss immediately raised his hand and gave the answer, to which the teacher came over and swatted him with a stick, all right, and beat him across the face. But what Gauss did was this. Supposedly, this is what he did. He said, okay, if that's the sum we're looking for, I'm going to rewrite the sum this way. I'm going to add these two up, and he did this in his head too, supposedly. So 2s is equal to but how many of these 101s do we have over here? We have, well, there's one, we have 100 of them. So s is equal to 100 times 101 divided by 2. And 2 goes into 150 times. So you got 50 times 101. And the answer is 50, 50, 5,050. Okay? Well, please note, This is exactly the formula that we have, and he derived this formula in doing this problem, where n is the number of numbers that we have, 100 numbers. N plus 1 is 101 divided by 2, okay? And that's what the answer would be. So the sum of the first 100 counting numbers, or integers, is n plus 1 divided by 2. And that's the formula for it, and that's what he did when he was in second grade.
Second grade.
Yeah. Supposedly, that's really what, it's a true story, supposedly. All right, this is a formula you should know. We're going to use this formula to do this problem. But there's another one that we're going to use in a minute, and that's this one. I'm going to give you one more of these. This, I don't expect you to actually memorize this, but we are going to use this. And that's the sum of the first squares, n squares. This is 1 squared plus 2 squared plus 3 squared plus n squared. And we're going to use this in a couple minutes. Oh boy, that must have been a good one, Nick. In Vitali. That's okay. That's okay.
It was really fun.
I'm sure it was. I'm sure it was. All right, that formula is equal to n. Wait, do you know this one too, Damien?
Yeah.
What is it?
Times 2n plus 1 over 3. The original times that, but it would be n plus 1 times 2n plus 1 over 6.
That's very nice. Over 6. Just what he said. It's the original one, n times n plus 1 over 2, times the 2n plus 1 over 3, which gives you this formula for the sum of the first n squares. Okay?
N plus 1.
n plus 1, 2n plus 1, all over 6.
Now where did the 2 n plus 1 come from?
It's the formula. To prove it, yeah, it's the formula. You could prove it with math induction, and that math induction is another discrete structures kind of a thing. If you were to be a math major and take discrete structures, or a computer science major, it seems to me, you would take discrete structures. And in discrete structures, one of the things you do is math induction. And you could prove this formula with math induction. This is a math induction formula. All right? So, did you guys do this one in there?
No, I'm doing that next semester.
Oh, did anybody take discrete structures already? No, wait, I don't think you can. I think the prerequisite is count 2. Yeah, okay, so that's why. Okay, so this is a formula we're going to use. You prove it in discrete structures. The proof is kind of neat. It's kind of cool. Any math proofs are just awesome. All right, but anyhow, they're awesome. The math proofs are awesome. I'll tell you, never mind. I won't tell you what you all should be. I won't tell you should all be math majors because that's not right. Okay, here's the sum of the first n squares, n plus 1, 2n plus 1 over 6. Okay? We're going to use that one. Here's one we're not going to use, but I have to show it to you anyways because it's so cool. And that's this one. The sum of the first n cubes. 1 cube plus 2 cube plus 3 cube plus 4.
3n plus 1?
No, that would be logical. What it is unbelievable. It's n plus 1 over 2. The sum of the first n squares squared. Not cubed, but squared.
Can you just write it with n squared times?
N squared, n plus 1 squared over 4. Yes. Yes, you could. It's amazing that that would be the case. I was always astounded. When I first saw this, I was just astounded that that would be the case. Okay, but anyhow, that's what the formula is. We won't use it, but I had to show it to you anyways. Okay, so here's what we have. We have some properties of the sigma notation. We can split these things up across sums, and that's what we've done. The sum of the n constants is nk, and the sum of the... Okay, so we have enough ammunition to do what we need now, okay? So you ready? Let's go back to the original problem. The original problem was this. I'm going to break it up. Because I can split these things up. I'm going to take the 7 out front. I can take constants out front. Okay? With me?
Why
And-
don't you bring the 3 up?
I could bring the 3 out front and have a 1 there. I could do that. That would be a reasonable thing. Okay? So what do we have? This first one, we have 7 times the sum of the first 100 integers, which is equal to n, 100, n plus 1 over 2. That's our 50-50 that we know from Gauss. Okay? Plus 300 added up 3 added up 100 times, which gives us 300. And again, you could take the 3 out front, like Nick said, and you have the sum of 100 times, which is 1 plus 1 plus 1, 100 times, which is 100 times the 3, or 300. We end up with an answer of, well, this is 50-50 times 7, plus the 300. And this is this 7 times this 5,000 will be 35,350 plus the 300. So it's 35,650. Of course, I did a bunch in my head, so who knows what the real answer is. I'm going to assume that that's the real answer unless somebody has something different. All right, Vitaly, what do you think? That's it? That away. So that's the kind of thing you want to do with those summations. Yes?
So the 7i, the I is, that stands for the first 100 integers.
This I, because of the notation, says start I at 1 and add 1 plus 2 plus 3. That's what the notation tells you to do. So that would be the sum of those first 100 integers. And that's the formula that I gave you before. Okay? All right, how are we doing? Gester, you doing okay?
Yes.
Jeff, you doing okay?
Yeah, I'm all right. Are we only doing section 2 today? Or?
No, we're going to do 3. We're here for a while. Oof, long time. Until the Super Bowl. All right, and then the Super Bowl, and then we go. All right. Go ahead.
So the formula that you use was n times n plus 1?
Divided by 2.
Okay.
Where n is equal to 100. That's what I used. Okay? How are we doing? Everybody okay with that? Course Compass is going to give you a bunch of those. Go ahead. Oh, okay. Course Compass will give you a bunch of those to do. All right? You just do them. Some you got to do by hand, some you got to use the formula. Okay? You can do it. Because I'm going to go on. You ready? What's that?
Did you say by hand?
By hand, yeah.
Oh.
Well, they'll give you a little, I mean, they'll give you the sum of the first 5 cubes, maybe. So it's 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube. Now, you can use the formula because the formula works. Okay? Or you could just do 1 cube plus 2 cube. You could just actually do it by hand. Okay? Do it out. All right? Or you could use the formula. What's the sum? Go ahead.
How come the I you replace with 100? And
Yes.
3 times 100.
Yes.
Aren't you supposed to use the same formula for that?
No, because I don't have an I here. It's just the sum of this constant 3 100 times. Okay?
And after that, 100 times 100, 100 plus
Say that again. I'm sorry.
7 times 100.
This 7?
No, father.
This 7?
No, no, no. Oh.
This 7? Where are you going? Come here.
7 sigma.
What do you want to do?
This, it's supposed to be a plus or times?
It's times. It's n times n plus 1 divided by 2. Okay? All right. Is everybody else set with this? It's the kind of thing Course Compass is going to expect you to do here. So make sure you're okay with this. I should give you one. I'll give you one. Let me give you guys one to do. Let's make sure. Here we go. Find the sum. One to 10. I don't know. 7 I minus 5. Yeah, we'll just keep it simple. Go ahead. Find the sum. You got it? Does that mean you got it, Jeff?
I think so.
Okay. Well, I just did it in my head, so there's no guarantee here, but I got, that's what I got. Nice. Okay, when you have it, raise your hand. Let's get a few people, and then then we're going to go on to the main business today, which is to find some area under a curve.
So is this all 5-2?
This is 5-2. I'm going to go on to 5-3 when I start doing the areas under a curve. This is all 5. 5-2 is just those summation problems. Okay. I'm going to go there. I'm going to go see who's got the right answer, okay? All right, you guys got it? Now, am I going to be embarrassed if I look at that screen? Probably. Oh. Yeah.
I got the same.
Yeah, I'm sure you did.
You're not gonna be embarrassed. Look at
I was a little bit concerned about that. Yes, sir, how you doing? You got it all right? Okay, looking good. Looking good. You're just about there. So Tyler never made it, huh?
this.
Tyler was the guy that was working with us over, he's the
IT dude?
IT dude, yeah.
He didn't email you?
Tyler, did he email me?
He didn't
Jeez.
drop out, did he?
What's that? I don't think so.
Yeah, but you missed class
But he
last
missed
time.
class like.
He missed class a lot last semester,
Yeah,
it's true.
well,
Does he get A's?
Yeah, he just,
Did he get an A? He didn't get an A.
no, he did good.
I don't think he did that good.
No?
He didn't do as good as you, Jeff. No, maybe he did. All right.
Slid right through.
Maybe he did. All right. That's perfect. Yeah, sure. Well, that you would do by hand. You could do a formula for it.
what was your answer?
Here, I can do one like that. The thing is this, people. Here, let me get, I'll show you what I mean. I'll give you one.
385. That's a minus 50.
All right, you guys ready?
Oh, it's a minus 50.
Yeah. So, you got it? Got it? How you doing? You got it?
No, I did add, but whatever.
Let's take a look, all right? All right, let's take a look. I would separate this. You could do this by letting I equal 1, and then 2, and then 3, and then adding them up. That's one way to do the problem, okay? Or you could do it by separating these things. I'm going to take the 7I, I'll bring the 7 out front. You could take the 5 out front, as far as that goes, okay, as well. Okay. Or leave the 5 in, it doesn't really matter. This is the sum of the first 10 integers here, okay? What's the sum of the first 10 integers? It's 10, that's n plus 1, 11 divided by 2. That's the formula for the sum of the first 10 integers. Okay, times the 7 that we brought out front. When we add up 1 10 times, we get 10 times 5 is 50. 2 goes into 10 5 times. 5 times 11, 55 times 7 is 385. Okay, 335. Gester points out a problem that's possible. Suppose you had a problem like this to do. Yeah, let's just keep it simple here. Let's not do I squared. Let's just do I. Okay, something like this. What would you do here to find out that sum?
Same thing you do with all of them, no? You move the one, suppose the one to the front, correct? Doesn't work for this one.
Would you have to subtract?
Yeah, the way to do it is to subtract.
But it wouldn't be, n would be 50, 51 divided by 2. No?
Yes, that's part of it. Here's what you would do. That is part of it.
7 times 8.
But what you would do is this sum minus this sum, like so. And doing it this way, you can use the formula twice. Okay? This goes from 1 to 50, this is 1 to 7, and subtract those from the ones 1 to 50. That's the way to do that problem.
Okay,
Okay.
I'm confused.
Okay.
The 8 would go into that 50, am I correct?
The 8,
How does that work, that 8 to 50, how does it work?
that would work by saying 8 plus 9 plus 10 plus 11 plus,
Oh, it's from
plus
8
50. Yes, that starts at 8 and goes up to 50.
Oh, okay, I see what it is.
So what you do is take 1 to 50 and then subtract off the 1 to 7 one. And that'll give you these. Okay, so that's one thing to be aware of. Okay? Yes?
What's the formula for that one again?
Say that again?
The formula?
The formula is for the sum of the first n integers n plus 1 over 2.
Okay.
Okay? All right, you ready to move on? Let's move on. Here's the problem. We're going to go right into it here. The problem is to find the area.
This is 5-3.
This is 5-3. Under y equals x squared from x as x goes from 0 to 1. We want to find the exact area under that graph of that function from 0 to 1.
So summation.
We're going to do it by summation. That's exactly what we're going to do. This is going to be a long process.
A is 0 and B is 1.
A is 0 and B is 1, yes. What'd you do? Did you finish the course, Damien, or what?
No, because like usually you just put the, in WebAssign it's the brackets and 0.
Oh, like this?
Yeah, I was just clarifying.
Oh, I thought you were doing the definite integral and doing the answer with the definite integral already,
Well,
which is what I'm going to end up doing at the end of this process. Okay. All right, so here's what we have. Now, that's a Y there, believe it or not. We want to find the exact area under this curve, okay, from 0 to 1. Well, we're going to do this in stages and steps. The first step we're going to do is to divide, we're going to do an approximation first. We're going to divide this area into 2 pieces, okay? And we're going to find the area as an approximation by summing up the 2 pieces that we get, okay? And then we're going to divide it into 4 pieces. And we're going to find the area 2 different ways with those 4 pieces. We'll get a boundary on the area. We'll get an approximation. Then what we're going to do is get the area in terms of n pieces. Okay? And we'll get an approximation in terms of n. Ooh, this sounds exciting, huh? And then we're going to let n go to infinity and see if we can evaluate the limit as n goes to infinity. If we can evaluate that limit as n goes to infinity, that limit will be the exact area. Because as we take more and more pieces, we get closer and closer to the exact area under that curve. In the same way we did with the tangent line, the slope of the tangent line. By taking the limit as delta x goes to 0, we got closer and closer approximations to the exact derivative or slope of the tangent line. And finally, when we took the limit, we got the exact slope of the tangent line. We got the derivative.
Is this a proof?
This is kind of a proof. This is not the real proof of showing the connection between the derivative and the integral as inverse operations. I'm going to do that on Monday.
Is this the harder way of doing it?
Oh, yes. This is much harder.
So
This
should,
is,
should we wait to do
oh,
that?
well, that's a good question, Nick, because what happened with derivatives, we had to use this limit process to find the slope of the tangent line first, but then we used that limit process to do properties of derivatives, and then we never need the limit process again. We used it to find those properties, and then we used the properties of a derivative to calculate derivatives. We didn't need the limit process anymore. It's similar to that. You're right. I'm going to do this long, tedious process, okay? By the end of it, you're all going to be like dead. And then we're going to do it in like one step. All right? And that's the process we're going to end up using. And on Monday, I'm going to prove why we can do that. And that's what we're going to do from then on. But I'm going to tell you this. I think it's important to understand the process. Why? I'll tell you why. There's several reasons. The main reason is we're going to use this integral to solve a great many problems in the next chapter. The next chapter is applications of the integral. We're going to do problems like take an area under a curve, revolve it around an axis, generate a solid of revolution, and find the volume of that solid of revolution. Or find the surface area of that solid of revolution. Or take a curve and find the arc length of that curve. Okay? Or take a region, okay, what we're going to call a lamina in a plane. A lamina is a plane region that has density. Think of it as a thin plate with some density per unit area. And we're going to find the centroid of that lamina, where that thing would balance on the head of a pin. And you know what? And we're going to find the work done. If we got a spring and we pull that spring, a certain amount of work is done. We're going to find the work exerted by that spring. We're going to do that kind of a problem. We're going to do a problem where if this is the top of the water and this is underneath the water, and we got certain fluid pressure on this thing. Now, if this is horizontal, it's easy. It's the area times the depth times the weight of the water, okay, density of water. But if we were to tilt this thing up, it's not easy anymore, okay? It's a little bit more complicated. And actually, if we had an irregular shape, it's a calculus problem. But every one of those problems is going to be solved by this infinite sum process. If we can take this problem that we have to solve and get it into the right form of an infinite sum called a Riemann sum, we can solve that problem with an integral. And that's why it's going to be important. Okay? So that's what we're going to do. All those problems can be solved that same way. And there are lots and lots of others that can be solved as well. You want to launch a satellite into an orbit, how much work is done? That's an integration problem. That's it. That's a problem. All right? There's lots and lots. So it's important that you understand it because it's the basis for solving all these other problems. All right? So that's what we're going to do. So let's do it. All right. The first thing is let's do an approximation. All right. We're going to divide this area into two pieces. Okay? So this piece, this point right here is going to be 1/2 0. Okay? Now, I'm going to use rectangles to divide this area up into rectangles. I've got two possibilities on my rectangles. I can use what are called right endpoint rectangles, which means go here and do this rectangle plus this rectangle. Those are right endpoint rectangles. And let's do this. Let's do that. Right endpoints. The area under that curve, in terms of these two rectangles, I'm going to put a little 2 there, is approximately equal to the sum of those two rectangles. Okay? Let's take a look at the first rectangle. First rectangle is this one here. It's got a width that's 1/2. Its height is this height here. It's f of 1/2, okay, the function at 1/2, plus the width of the second rectangle, 1/2, times its height, which is f of 1. Okay, you with me on this? Okay, this area in terms of two rectangles is 1/2 times f of 1/2, which is 1/2 squared, plus a 1/2, and this f of 1 is a 1 squared. Okay? And this is equal to a 1/2 times 1/2 squared plus 1 squared. Okay, you with me? I took a 1/2 out of each.
So is f the
F is the function, f of x is x squared.
oh,
Another way of writing it, same thing. So what do we end up with? The area of two rectangles is 1/2, and we get 1/4 plus 1, okay, which is equal to 5/4, which is 5/8. Okay? That's my estimate as to what this area is. Now, how good an estimate is it? Is this estimate, first of all, too high, exactly equal, exactly right, or too low?
Too high.
It's too high. There's excess area here. So we know this area is too high. Well, tell you what, let's do another approximation. let's take two rectangles, but let's take left endpoint rectangles. All right? So here we go. Let's take left endpoints. Same problem. Divide into two pieces, but now we're going to take left endpoints. That means the first rectangle here is 0, okay, 0 height, and the second one is this one here. So the area of these two left endpoint rectangles is approximately equal to this width of 1/2 times the first height of 0 plus second one, its width is 1/2, and this height, using the left endpoint, is equal to the value of the function at 1/2. We already know that's 1/4. So that's equal to 1/2, 0 plus 1/4. That's equal to 1/8. Okay? The 1/4 is this height right here. This point is 1/2 squared, which is 1/4. And that's the height of the second rectangle. The first rectangle has a height of 0 because I'm using the left endpoint. Okay, so that height is 0. This height, the second rectangle, is this here, which is the value of the function at 1/2, which is 1/4.
Yeah, but how do you know half it's going to be a half?
I'm dividing it up into two pieces, two equal pieces.
Oh.
So I'm going from 0 to 1 and taking right in the middle, 1/2. Okay? So that area is 1/8. Now, is that area too high, exactly right, or too low?
Too low.
It's too low. Okay? Actually, we could get a pretty decent approximation by adding the 2 up and dividing by 2.
Yeah.
And if we added the 2 up and divided by 2, we'd be using trapezoids in that case. And a trapezoidal rule is a really good way of approximating that thing. But we're going to use rectangles. We're going to stay with rectangles.
Adding those two up. Adding what?
The two rectangles that we got, if I add those 2 up and divide by 2, it's the same thing as taking this, well, it'd be a triangle in this case, and then this one here, which is, here's my big rectangle, here's my small rectangle. If I add them up and divide by 2, I end up with a trapezoid here.
Okay.
Yeah, and we could do that, but we're going to use rectangles. Okay, so far we've used 2 rectangles, right endpoints, left endpoints. We've got 2 approximations, 5/8 and 1/8. How could we do better? We could do better by taking more rectangles, and that's what I'm going to do. I'm going to take 4 rectangles this time. Here we go. You ready? 4 rectangles. Okay, n equals 4. I'm going to do 4 rectangles. I'm going to do right ones and I'm going to do left ones. And we're going to see, we're going to get better approximations. Here we go. This is something, you just have to go through when you do this calculus stuff here.
It's sort of like, almost like pixels.
Yeah.
0.1 pixel, 0.2, just
That's
getting
how-
finer and finer.
Yeah, that's how cameras and displays work.
Yeah, that's it. Let's divide it up into 4 pieces. 1/4, 1/2, 3/4. Okay, this is 1, this is 0. I'm going to do right endpoints first. My area, in terms of these 4, is approximately equal to the width of 1/4. First rectangle, my right endpoint rectangle is this guy. The height is the value of the function at 1/4. Okay, that's this rectangle. Plus, next rectangle, width is 1/4. The height is the value of the function at 1/2. That's this rectangle. Plus 1/4 times the value of the function at 3/4. Plus, that's this one. The last one, 1/4 times the value of the function at 1. Okay? Whew. I tell you, I'm working like a dog here, okay? I'm using up calories as many as when I play racquetball. No, that's not true. I don't think it's true anyways. Okay, everybody okay so far? Okay, here we go. So, in terms of right endpoints, we're n equals 4. The right endpoints. My area is approximately equal to. Now, I can take out a fourth out of everything. Now, I get f of 1/4. That's 1/4 squared. That's 1/16 plus 1/2 squared. That's 1/4. I'm going to write it as 4/16 plus 3/4 squared, 9/16 plus 1 squared is 1. I'm going to write it as 16/16. Okay? This is equal to 1/4 all over 16. I've got 5, 14, 30. Okay? I've got 30 sixteenths, okay, which is 30 over 64, okay, which is equal to, when I divide by 2, I get 15 30-seconds. Okay? A little bit less than 1/2. Okay? Now, that's an improvement on what I had before. What I had before was 5/8, which is greater than 1/2. Now I get something less than 1/2. I've cut that down, okay? Now, it's still too great because I have excess area on these rectangles, okay? But it's a little bit less excess. In other words, I got a better approximation here. In other words, my error is decreased, has decreased, okay? By taking these 4 rectangles.
So
Now,
it's almost like where summation, you keep adding.
that's what I'm going to do. Well, you know what I'm going to do next? I'm not going to take rectangles, which I could do, okay? I'm going to do n rectangles, and then I'm going to let n go to infinity. And we're going to evaluate that limit. And if we can evaluate the limit, and if we find the limit as n goes to infinity of the right endpoints is equal to the limit as n goes to infinity of the left endpoints, we have the right endpoints, its area approximation coming down. The left endpoints will be coming up. And if they're the same limit, that is the exact area. Okay? That's what we're aiming for.
But wouldn't that be almost impossible?
What's that?
Squares, if they keep getting smaller and smaller and smaller and smaller and smaller, technically speaking, it can't be possible.
It's possible. We will do it. We are going to do the impossible. All right? We are going to add up an infinite number of things going to 0. That's what we are going to do because we have power. Okay? All right, let's do it. All right, that's right endpoints. We're going to have to do left endpoints. All right, here we go. N equals 4 still. But now we're going to do the left endpoints. Now, let's see. 4 of them. All right, can we abbreviate this process a little bit here? Let's see if we can make this a little less tedious. What's the width of each one of those? Here, let me draw it out here. Let me draw it out here. Oh boy, I'm getting worse and worse now. All right. I'm still dividing this into 4 parts. But now with the left endpoints, I'm starting here and going this way. Okay, there's my 4 rectangles now with my left endpoints. Okay, what's the width of each one of these rectangles? 1/4, okay? I'm going to take the 1/4 out, just like I did here. Now, what's the difference between this one and this one? This one, the first one, was 1/16. It was the height of this function at 1/4. This one, what's my first height? 0. What's my second height? 1/16. And what's my next height? 4/16. And what's my next height? 9/16, and that's it. The difference between the two is this. This one we start at 0, and we end at 9/16, the one just before the end one here. Okay? Now, what's our sum equal to? Let's see. Well, let's see what we got. We got 1/4, and add up all these 16ths. Okay? We got 14/16, okay, which is 14/64, which is equal to 7/32. Now, that's greater than what we had before. What we had before was 1/8. Now we've got 7/32, which is, geez, almost 2/8. Wow. No, we've gained. We went from 4/32, 1/8, to 7/32, so we jumped up. So the left endpoints are increasing, the right endpoints are decreasing. Go ahead.
I'm a little confused.
Go
What
ahead.
do you mean by left and right endpoints?
Okay, so when I divide this up into rectangles, okay, I can do my rectangles. How do I get the height of these rectangles? I can start with this left endpoint, which first height is 0. This height is, starting with the left endpoint of this one, is this.
So how'd you get that 1/16? I got that out to 1.
This 1/16
Yeah.
is because that is this height right here, which is, this point is 1/4, 1/16. This height is 1/16. And that's my second rectangle when I'm using the left endpoints.
Where at the right you started off.
At the right, I go to the right endpoint and I draw it back this way, and that's my first height. That's my first rectangle. Okay? So from the left, my first rectangle is 0 height, but from the right, it's equal to that 1/16 height. Okay? And see, when I did the right endpoints, my last one is this one. But from the left, it's this one. Okay? Okay. All right. I don't want to do any more rectangles. I mean, I don't want to. I could do 8 rectangles, and guess what? We would see that the right endpoints comes down some, and the left endpoints increase some. Okay? They're headed towards the same thing. But here's what we're going to do now. We're going to do this in terms of n rectangles. Right endpoints and left endpoints. And then what we're going to see if we can do the limit as n goes to infinity. That's what we want to do. Let's do it. Holy mackerel, I got 50,000 pages of notes here. That's because I'm using this pen, because it's easier to see this pen, but it's you know, it's just bigger.
Pens.
What's that?
How many your other pens?
I have other ones. I don't know where they are. But I'm using this in Calc 3 because I have one person in there who's getting new glasses and she can't see anything. So this is big enough so she can see the thing. So
It does help. It's nice.
yeah, so I'm using it. All right, so here we go. You ready for this now? I can see that. Oh, wow. We got plenty of time. Here we go. Okay. I'm going to divide this up into n equal pieces. Okay. I need the coordinates of this point right here. If I divide this up into n equal parts, what's the x coordinate right there? What is it? 1 over n is correct. What would the coordinates of this piece, this point, be right here? Very nice, thank you. And what would be the coordinates of this piece, this point right here? Jeez. 3 over n. If I divide this up into n equal parts, the width of each part is going to be 1 over n. You divide 1 into n parts, 1 over n, 1 over n, another 1 over n, 1 over n, 1 over n. Each piece is 1 over n. When I divide it into 4 parts, 1/4, 1/4, 1/4, 1/4. If I divide it up into 8 parts, 1/8, 1/8, 1/8, n parts, 1 over n, 1 over n, 1 over n. So this point is 2 over n because I have a 1 over n and another 1 over n, and then another 1 over n, etc. Here's what I need from some intelligent student. What are the coordinates of this second to last point here? The last point is 1 and 0. What about this one?
N minus 1 over n.
Perfect. Thank you. Okay? Thank you. That was good. Vitaly, that was good. Oh, I think, Nick, I think it was great. Okay. All right. Let's do the area in terms of right endpoints, in terms of these n rectangles. So in terms of right endpoints, n of them, I'm going to have this approximation. Okay. First of all, what's the width of every one of those rectangles? 1 over n. I'm going to factor that out. Okay. My first height of this rectangle, my right endpoint rectangle, is going to be the value of my function at 1 over n, which is going to be 1 over n squared. Plus my second rectangle, this one. This is its height. It's the value of my function at 2 over n. It's 2 over n squared. My third one is going to be this height. It's going to be 3 over n squared. Okay? My last rectangle, my last right endpoint rectangle, its height is going to be, is it going to be what? No, well, that would be the second. That would be the second to last one. That would be this guy right here. That would be the one whose height is. The last one is going to be this one here, which is going to be 1. And I'm going to write the 1 in the form of n over n. Okay. Okay, how's that look? In terms of n rectangles, this will give me the area under that curve. Let's do left endpoints. Each one is still 1 over n. But now, what's my first height? 0. Now, what's my next one? And then the next one. Now, what's the last one here?
N minus 1 over n squared.
Yes. Okay, that would be the last one. It's the second to last one of the above one. Okay, those are my two approximations. Okay? All right. Believe it or not, what I want to do, first of all, let's simplify a little bit here. We have some simplification here. Let's simplify a little bit. Let's do the right ones. What can I do here? Well, every one of those terms is over n squared, so I can write it this way. Okay? I can write it that way. It's all over n squared. And my left ones, starts with 0. Okay? Okay, those are my approximations in terms of n. What I really want to do is now take the limit of each as n goes to infinity. Okay? I'm going to take this limit. So, my area under this curve is equal to the limit as n goes to infinity of this sum Now let's deal with this one first, and then we'll deal with the other one. The other one's a little bit more complicated. All right, how are we going to evaluate this sum? Let's take a look at this. Well, 1 squared plus 2 squared plus 3 squared plus all the way out to n squared. What's going on with that sum as n goes to infinity? Where's that sum headed? To infinity. Yeah, that's just increasing without bound. The denominator here is n cubed. as n goes to infinity, that's also going to infinity. We have a numerator going to infinity. We have a denominator going to infinity. We have infinity over infinity in determinate form. It's like the 0 over 0 indeterminate forms you used to get all the time in Calc 1 when you did this limit, applied that limit process to the derivative. You got 0 over 0 all the time, and what did you have to do? You had to change it somehow. All right, you had to change it to eliminate that 0 over 0 thing. You changed it somehow by multiplying things out, by rationalizing denominators, by doing something, eliminating complex fractions, doing something. All right, here's what we're going to do. Let's take a look at this. 1 squared plus 2 squared plus 3 squared plus n squared. We have a formula for that. We can replace that sum with the formula for the sum of the first n squares. Damian gave us that formula a while ago. That formula was this. What's the sum of the first n squares? It's n plus 1, 2n plus 1, divided by 6. That's what the formula gives us for the sum of the first n squares. Okay?
I have a question.
Go ahead.
Where'd you get the cubed and, I'm sorry, I kind of got.
Where did I get the what?
The cubed, uncubed.
Where's the n cubes? I don't have any n cubes.
You going to?
Oh, I'm going to. I'm going to in a minute. What are you, ahead of me or what? Yeah, I'm going to multiply n times n squared to get n cubed.
But you can just cancel it.
No, the n squared, sorry.
This n squared right here?
No, the one before that.
This n squared here?
Above it, yes. No,
This-
the numerator, the denominator.
The denominator is from here. See, what I'm doing,
That part, where did that come from?
this n squared here?
Yes.
It came from all these n squares.
Well, n's.
These are all n squares. These are 1 over n quantity squared. That gives me 1 squared over n squared, 2 squared over n squared. I'm doing the right endpoints now, okay, people? I'm just doing right endpoints. I'm just taking this formula up here, and I'm putting it down here, and I'm going to do the limit as n goes to infinity on this formula. It's a little bit easier than the other formula, okay? But I'll do the other formula in a minute. And what I'm doing is saying, okay, here's the sum of the first n squares. I have a formula for the sum of the first n squares. It's this, okay? So what I have now to do is evaluate this limit. Okay. Now, one thing you did in Calc 1, you did limits like this, okay? You did limits like this, where you have the degree. Wait, you remember this, right? We did those limits? Yeah. We did those where we have same degree, numerator and denominator, and we said the limit as n goes to infinity is equal to the ratio of their leading coefficients. Ooh, here, I'll show you what I'm going to do here. I'm going to multiply this out. I think it's easier to see if I multiply it out. Let me multiply this out. I've got n times n plus 1 times 2n plus 1. N times n plus 1 is n squared plus n.
Why don't you cancel the ends out first?
Ugh, it's illegal. You mean reach in here and do this, this, and this?
No, just that n that's already factored out.
Oh, yeah, I could do that. Nice.
Wouldn't that be so much?
That's nice. I agree with you totally. I have an n and I have an n cubed. What the heck? Cancel them out. Do what he said. Very nice. Oh, geez. And then not do it, okay?
Why don't you just stick that n and make it a cube then?
I could have canceled them out here. Yeah, I could have done that. That would have been a little bit smarter. You're right. I could have done it. But anyhow, this is what I end up with. Good call. Good call. Both you guys. All right, let me multiply that out. Take the limit as n goes to infinity. 2n squared plus 2n plus n plus 3n plus 1 over 6n squared. Now, we did problems like this in Calc 1, those kinds of limits as n goes to infinity. And we said that that limit is equal to the ratio of their leading coefficients. Do you remember such a thing in Calc 1? What's that? So it's equal to 2, 6, 1/3. You can prove it by dividing numerator and denominator by n squared. Let me do that, okay? I'm going to divide numerator and denominator by n squared. I'm going to have a 2 plus 3 over n plus 1 over n squared over 6. I'm going to divide each of these by n squared, divide this by n squared. The point is to get n squared in denominators, so when it goes to infinity, I'm going to get zeros. This will be a 0 as n goes to infinity. 3 divided by n as n goes to infinity is 0, and this is also 0. I end up with 2 6ths, 1/3.
If the numerator was greater, that means it would go to infinity.
Correct. And if the denominator was greater degree, it would be going to
0.
0 is correct. Very nice. Good deal. All right, so here's what we got. When we do our right endpoint rectangles, and we let n go to infinity, so the number of rectangles goes to infinity, increases without bound, we get a limit of 1/3. That is the exact area under that curve. And now what we're going to do is confirm that by taking the other limit, the left endpoint rectangles, and finding that limit as n goes to infinity. And hopefully, what are we going to get for an answer? A third. The same thing. And that would seal the case. Because we have this limit going to 1/3, that limit going to 1/3, they're going to the same thing. The area must indeed be equal to 1/3. So let's do it. Let's take the other one. So I'm going to go for the left endpoints. Recall what I had there. I had 1 over n, 0 squared, 1 squared, 2 squared, n minus 1 squared over n squared. Now, I'm going to take the limit as n goes to infinity. And I'm going to replace this sum with the formula for it. Now, what's the formula of the first n squared? The formula for the sum of the first n squares is n plus 1, 2n plus 1 all over 6. But what is n in this case? I'm finding the sum of the first n minus 1 squares now. So instead of having an n, the formula of n plus 1, 2n plus 1 over 6, the number of squares I have is n minus 1. So I'm going to use n minus 1. It's what I'm using for n now. I've got n minus 1 squares instead of n squares. So I'm using n minus 1 in the formula. n, okay, n plus 1, 2n plus 1 over 6. That's what the formula gives me.
N plus 1?
2n plus 1.
No, how did you get the second one?
The second one is n plus 1. The formula is n plus 1, 2n plus 1, all over 6. But what's n now? N minus 1, because I'm finding the sum of the first n minus 1 squares.
Sorry, repeat that again.
Yeah, I know, it's a little tricky. I gave you a formula for the sum of the first n squares. And that formula is n plus 1, 2n plus 1, all over 6.
Well, I got that part.
Okay, now I want the sum of the first n minus 1 squares.
No, why is it n minus 1? That's n.
Why is it n minus 1? Because that's what the left endpoints gave me, an n minus 1 at the end.
And then it's n minus 1 plus 1, so should
Yeah,
it
but
be
what
n
about the
minus
rest
1
of them?
plus 2?
What's that? This one here?
Yeah.
Here. The formula is, here's the formula for the sum of the first n squares. It's n plus 1, 2n plus 1 all over 6. That's the sum of the first n squares. But now I've got n minus 1 squares. So instead of using an n, I'm going to use an n minus 1. You've got to replace this with n minus 1, replace this with n minus 1, replace this with n minus 1, and that's what I've done.
No, see, what I'm confused about is
Okay.
because you had 1 squared, 2 squared, and you only had n minus 1 at the end, not for the whole thing. So that's why I'm confused why you would be using n minus 1 for the whole equation.
Because that's how many squares I have to add up. I've got n minus 1 squares to add up.
I think I'll get it.
Another way to do that, but it turns out to be more complicated, is to actually add n squared and subtract it. So you use the formula for n, but then you subtract n squares from it. This is the way to go.
Okay.
This is the way to go. I'm replacing n with n minus 1 is what I'm doing. Okay. So what do we get? We get the limit as n goes to infinity, 1 over n. Let's see what happens here. I end up with an n minus 1, n minus 1 plus 1, which is n, a 2n minus 2 plus 1, which is a 2n minus 1 all over 6. Okay. That would be my formula.
Would it be 0? No? 2n?
Which one?
2n minus 1 plus, 2n plus minus,
This would be 2n minus 2 plus 1.
okay.
Okay? And now I'm going to do this a little bit smarter than I did before. I'm going to cancel out these n's. Okay? And I'm going to multiply that numerator out. Wait, hold on a second. That's this. Okay, hold on. I've got my n squared still sitting here. Okay? That's my n squared still sitting here. I got my n squared there. So now I'm going to multiply this out, and I'm going to get 2n squared minus 2n minus n, minus 3n plus 1 over 6n squared. And what's that limit as n goes to infinity? 1/3 again. I get the same answer I got from before with my left endpoint ones. The same limit. That proves that the area under that curve is 1/3. Now, here's the deal. It just took me a while to do that. All that stuff that I've just done can be replaced by this. Watch this. Instead of doing what I just did, here's what we could do. We could integrate x squared, and what I'm going to do is put limits of integration on here from 0 to 1. Okay? This is now called a definite integral. And what you do with this definite integral is find the antiderivative or integral of x squared, which we know is x cubed over 3. And what you do is replace the x with 1 and subtract replacing x with 0 to get 1/3. This, what I've just done here, replaces all that infinite sum. That integral is an infinite sum.
That's why it's an elongated f.
Yeah, that's why it is, because this is related to this, but you elongate the sigma to an s for the sum. It stands for sum. Okay?
Can you run that again? Do it again.
All right, I integrated x squared.
Yeah.
The integral we know from our rule is x cubed over 3.
Right.
And then what you do for the definite integral, you replace x with 1, and you replace x with 0, and you take their difference.
Wait, where did that 3 come from? I got the top 2. Where did the bottom 2 come from?
When you do that rule, it's x to the n plus 1 divided by n plus 1. That's the rule for x to the n.
So in any interval, you can take the integral and find.
Let's do it.
Okay.
Here's what we got.
Can we do one of the ones that we just did?
What's that? We only did that one.
Yeah, but this one.
That's what we just did.
That's the one.
Okay.
That's it.
All right. What do you want me to do? I'll do whatever you want me to do, Melissa.
Do any f of x.
Yeah, I'm going to do a no. Here, instead of 0 to 1, let's suppose we have the same problem.
What did you, before you?
Yeah, go ahead.
That 1 and 0, you just put that,
Magic.
how did that happen?
Because we were going from 0 to 1.
We're going from 0 to 1.
Yes. And let me do this one. Suppose we had this one to do. Let's go from 2 to 3. Suppose we need the area under this, y equals x squared, same function, but now we need the area from 2 to 3. How do you do that? Well, that area is going to be equal to the integral from 2 to 3. Okay? This gives you left endpoint, right endpoint of x squared. That's the definite integral that would give us that area. X cubed over 3 from 2 to 3. Substitute in 3, you get 27 cubed. Minus, substitute in 2, you get 8 cubed, 8 thirds rather. Okay, 27 thirds minus 8 thirds gives you 19 thirds. That's the exact area under that curve. What? No, Nick, we can't. And no, that's not just for squares, though. Now, what's that? What do you need? Okay. That's for any function. So if you had to do this one, now we just did the squaring one, and suppose you had this one to do. Do a square root one. And let's go from 0 to 4, say. Bless you. Okay. I'll tell you what, if you try the infinite sum process on this, you've got a problem. The reason you've got a problem is we don't have a formula for the sum of those first n square roots. We had it for the squares, and we took advantage of it. That enabled us to take 1 squared plus 2 squared plus 3 squared plus ... plus n squared and replace it with n plus 1, 2n plus 1 over 6. If we didn't have that formula, we have no hope of evaluating that limit. But that formula gave us that ability to do it. With the square roots, we don't have that sum. Okay? But what happens with the integral? It's this simple to find the exact area under this curve. Okay? This is x to the 1/2. Add 1 and divide by 3/2, which is multiplied by 2/3 from 0 to 4.
N is the exponent, am I correct?
What's that?
N is the exponent.
Yes, you are correct. And so you get 4 to the 3/2. 4 to the 1/2 is 2, the square root of 4. Cubed is 8 times 2, 16 thirds. That's the exact area under that curve. 16 thirds square units. Bless you. Okay? It's that simple. Okay? Okay? It's that simple to find the exact area under those curves. Okay? And we're going to do a lot of those. Go ahead.
So you showed us the process so that we understand how we're going to be doing the process using that. Or do we have to use the other process?
No, I'm not going to ever ask you to use that limit process. The book does, course compass does, though. It says use the limit definition to evaluate. But I'm going to tell you
How
this.
does it know if you do it or not?
It doesn't. All right, it does not. So I don't recommend that you actually use the limit process. Just use the integral. It works. But I want you to understand there is a connection. And on Monday, what I'm going to do is prove that connection between the integral and the derivative as an antiderivative. And I'm going to do a little proof there showing you that there is a connection between the two. But before we do, there's one other thing here, and this is this. I want you to realize that the sum we ended up with, okay, that area was equal to this limit as n goes to infinity of the sum from 1 to n, and we had our function times a delta x here. Okay, that's what we had. That delta x is the little width of each rectangle. Okay, it was that 1/4 when we had 4 of them. It was the 1 over n part when we had n of them. Okay, this sum is going to be very important. Okay, if we have a problem to solve and we can get it set up like this, in this form, we can evaluate this with an integral. Okay, this is the area under that curve, and that's equal to this integral. This sum is called a Riemann sum. Okay, it's a Riemann sum. Riemann, monster. He was an awesome mathematician, middle 1800s. His problem, that Riemann's problem of complex numbers, is the problem that drove what's his name mad, John Nash, mad, the guy who's a Beautiful Mind guy, the movie, you know, which I'm sure you guys watched several 100 times, like I did. All right, but that Riemann integrals, Riemann sums. Riemann was a mathematician in the 1800s that took the calculus and said, here's when we can apply it, here's when we can't apply it, this is what we must do. He was an amazing mathematician, certainly one of the top 10 of all time. All right, but anyhow, if we can get a problem and resolve it into this, to look like this, which is what we just did with the area, okay, then we can evaluate it with an integral. Okay? And that's what we're going to do in the next chapter when we have to find centroids of laminas of density, when we have to find work done by a spring, or the work done, or the fluid pressure on an object submerged in the water, or find the volumes of solids of revolution, or the surface areas of these solids, or arc lengths of curves. All these processes can be reduced to this summation and can be evaluated with an integral. And that's what we're going to do. All right, hopefully,
Was that 5.2?
5.3.
Really?
5.2.
What was 5.2 then?
The sums, those little other sums, this is 5.3 when you use it to do definite integrals. And you're going to have the definite integrals.
Are you going to put study on? Oh, yeah, you probably should stop recording.
Rectangles.
Okay, any questions?
Yeah.
You got a question?
No.
Oh, no. All right, see what you can do with the homework. Hopefully you can do the homework. If you have any questions, we'll do them on Monday, and we'll go on from there.